Since time immemorial, mankind has asked itself a question that arouses great fascination. What lies beyond what we know? What exists beyond the limits of our universe? The answer is extremely complicated, yet the James Webb Space Telescope has discovered something massive and fascinating in the far reaches of the cosmos that could revolutionize physics. What exactly has James Webb found at the edge of the universe? Why are scientists so excited? We invite you to join us to explore how this telescope has discovered something gigantic at the limits of what we can observe. If you are interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, like this video, and turn on the notification bell. Albert Einstein developed the theory of gravity that revolutionized Newton's theory in 1916. When he applied it to the universe, this theory showed that the universe could not stand still and must be in motion, expanding or contracting. In 1929, the astronomer Edwin Hubble observed that galaxies were moving away as a result of the Big Bang, which is the expansion of the universe where the distance between galaxies is constantly increasing. Einstein's theory can easily explain an infinitely expanding universe or one that curves back on itself like the surface of a ball in a higher dimension. Some argue that the universe has an edge since it was born in the Big Bang 13.82 billion years ago. As planets and other stars in their habitability continue to be studied, we do not yet know what the telescope will observe when it is pointed toward the edge of the universe. The universe is divided into the observable and the unobservable, with the observable being everything we can see by detecting radiation with our eyes. The limit of the observable is the cosmic microwave background that was produced 13.8 billion years ago. At that time, the universe was opaque like a dense fog. Some experts believe that there are gravitational waves and neutrinos coming from even more distant places, although this cannot be verified due to a lack of technology. Cosmologists suggest that to better understand the universe, one must consider that what we observe is only a small part of a larger reality. Finding galaxies like a 2744 Y1, which lies at the farthest edge of the universe, can help us better understand this reality. Although this galaxy is so far away that it takes 13 billion years for its light to reach us, scientists can observe its youth from 650 million years ago. The Spitzer, Chandra, and Hubble telescopes work together to discover this galaxy, as each uses different parts of the electromagnetic spectrum to capture data. By combining data from all three telescopes, astronomers can detect galaxies that are up to 100 times farther away than any telescope could have observed on its own. Astronomers from the Astrophysics Institute in the Canary Islands and the University of La Laguna used the Hubble Space Telescope to discover the galaxy A2744 Y1 and calculate its distance and number of stars. Using Spitzer equipment, they also employed the gravitational lensing technique, which acts like a magnifying glass that focuses light from distant galaxies through galaxies closer to Earth. The galaxy is small compared to our Milky Way, with a width of about 2,300 light-years, but its star creation rate is 10 times that of the Milky Way. The redshift of the galaxy A2744 Y1 is 8, indicating that its light has been pushed toward redder wavelengths due to the expansion of the universe. Before the discovery of a 2744 Y1, the farthest known galaxy had a redshift of more than 7, but now astronomers have found something even farther out, a supernova called DS16C2M, identified through a dark energy survey. Supernovae are incredibly massive explosions representing the last effort of a star before it dies. To understand how stars work, we must observe their deaths. Massive stars burn enormous amounts of nuclear material in their cores, generating large amounts of energy. This energy creates pressure that prevents the star from collapsing. When the star runs out of fuel, it begins to cool, and the pressure decreases, allowing gravity to take over and cause the star to explode into a supernova. This process happens quickly, in a matter of seconds. When two stars collide, a supernova can also occur. The DS16C2M supernova is extremely rare and was discovered in 2016 by a multinational team of astronomers. This star is a Type II supernova, which means it has reached the end of its life and exploded in a cataclysmic explosion. The explosion is believed to have occurred about 10.5 billion years ago, and light has traveled to us for more than 3/4 of the history of the universe. Due to the expansion of the universe, the supernova is much farther away than it appears to the naked eye. The DS16C2M supernova was particularly interesting because it was a dark supernova, meaning it did not emit much visible light and therefore was difficult to detect. However, it was possible to detect it using telescopes that could see the infrared light emitted by the supernova. A team of scientists involved in the discovery of DS16C2M also had the help of 3 powerful telescopes, including the Mellon Telescope and the KEK Observatory. It took 5 years and more than 500 nights of observation to identify this distant supernova, which was a great challenge. However, the team's effort was worthwhile, as the great distance of the supernova will allow them to better study and understand superluminous supernovae and the causes behind these massive cosmic explosions. A supernova explosion of the magnitude of DS16C2M or any other Type II supernova would have significant consequences for the surrounding galaxy and potentially even for the entire universe. This explosion would release an enormous amount of energy, primarily in the form of neutrinos and photons, which would interact with the surrounding gas and create a shock wave that would travel outward at speeds of thousands of kilometers per second. This shock wave would cause the surrounding gas and dust to heat up and emit a burst of radiation detectable across a wide range of wavelengths, including visible light, radio waves, and X-rays. In addition to the burst of radiation, the explosion would also create heavy elements like iron, gold, and platinum, which are essential building blocks for planets and life as we know it. These heavy elements would be dispersed into the surrounding galaxy, enriching the gas and dust and providing raw materials for future generations of stars and planets. Overall, a Type II supernova explosion like DS16C2M would have far-reaching consequences for the surrounding universe and play a crucial role in shaping the evolution of galaxies over time. Through analysis of the ultraviolet light emitted by the superluminous supernovae, scientists can determine the amount of matter produced and the temperature reached in the explosion, which is crucial to better understand these events. A difference between that star and Betelgeuse is their type of supernova explosion. DS16C2M is a Type II supernova, which occurs when a massive star runs out of fuel and collapses on itself, causing a catastrophic explosion. Betelgeuse, on the other hand, is expected to eventually become a Type II supernova but is currently classified as a red supergiant and is likely to explode as a Type IIP supernova, which is a less powerful and less catastrophic type of supernova. A supernova explosion of the magnitude of DS16C2M or any other Type II supernova would have significant consequences for the surrounding galaxy and potentially even for the entire universe. Now, experts are looking for other distant supernovae and those that are likely to be discovered in the future. What do you think lies beyond the edge of the universe? The search for understanding beyond our observable universe leads us to confront fundamental questions about existence, the nature of reality, and the very fabric of space-time. Theoretical physicists and cosmologists grapple with hypotheses that extend beyond our cosmic horizon, pondering whether space-time stretches infinitely or loops back upon itself in dimensions beyond current comprehension. This pursuit of knowledge propels advancements in observational astronomy, pushing telescopes like the James Webb Space Telescope to peer deeper into cosmic history than ever before. Each discovery, whether it's the cosmic dawn, identification of distant galaxies, or the observation of ancient supernovae, offers glimpses into epochs long past. These findings provide crucial clues about the origins and evolution of our universe, expanding our scientific knowledge and fueling speculation and further investigation into the vast mysteries that lie beyond the reach of current observation. One of the tantalizing aspects of the universe is its sheer vastness. The observable universe, which extends as far as light has had time to travel since the Big Bang, spans billions of light years. Yet beyond this observable horizon lies the unobservable universe, regions where light has not yet reached us due to the expanding fabric of space-time. The cosmic microwave background, a faint glow permeating the universe, offers a snapshot of the universe's infancy, revealing its early conditions and providing a backdrop against which galaxies and cosmic structures form. The James Webb Space Telescope, poised to succeed the Hubble Space Telescope, promises to revolutionize our understanding of the early universe and its evolution. Equipped with advanced infrared detectors, Webb will probe deeper into space and time, capturing light from the first galaxies that formed shortly after the Big Bang. This unprecedented capability will allow astronomers to study the cosmic dawn, a period when the universe transitioned from a dark, opaque state to one illuminated by the glow of the first stars and galaxies. In the quest to understand the universe's origins, scientists study phenomena like gravitational waves and neutrinos. These elusive signals, generated by cataclysmic events such as colliding black holes or supernova explosions, offer windows into the most extreme and energetic processes in the cosmos. While gravitational waves ripple through space-time itself, neutrinos, ghostly particles with almost no mass, traverse vast distances largely unaffected by cosmic obstacles. Detecting and interpreting. These signals require sophisticated instruments and international collaborations, pushing the boundaries of technological innovation and theoretical physics. Astronomers employ a variety of observational techniques to explore the universe's distant reaches. The phenomenon of gravitational lensing, predicted by Einstein's theory of general relativity, acts as a cosmic magnifying glass, bending and amplifying light from distant galaxies. This effect allows astronomers to study galaxies and cosmic structures that would otherwise be too faint or distant to observe directly. Combined with advancements in ground-based observatories and space telescopes, such as the European Southern Observatory's Very Large Telescope and the Atacama Large Millimeter/Submillimeter Array ALMA, these tools enable astronomers to probe deeper into the universe's depths. The study of distant galaxies provides insights into cosmic evolution and the formation of structures on the largest scales. By observing galaxies at various distances and epochs, astronomers can trace the evolution of stars, gas, and dark matter over billions of years. Galaxies like a 2744 Y1, discovered by the Hubble Space Telescope and studied with follow-up observations from ground-based telescopes, offer glimpses into the universe's early epochs. These observations reveal galaxies in their infancy, undergoing rapid star formation and harboring conditions that may resemble those of the early universe. The discovery of distant supernovae, such as DS16C2M, sheds light on the explosive deaths of massive stars and their impact on cosmic evolution. Supernovae are among the most energetic events in the universe, releasing vast amounts of energy and synthesizing heavy elements essential for planet formation and life as we know it. By studying supernovae across cosmic distances, astronomers can explore the universe's chemical enrichment and understand how these explosive events shape galaxies and their surroundings. The classification of supernovae based on their light curves and spectral characteristics provides insights into their underlying physics and origins. Type II supernovae, like DS16C2M, occur when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse triggers a catastrophic explosion, ejecting stellar material into space and leaving behind compact remnants such as neutron stars or black holes. Type Ia supernovae, in contrast, occur in binary star systems where a white dwarf star accretes material from a companion until it reaches a critical mass, triggering a runaway nuclear fusion reaction. The study of supernovae is crucial for understanding the universe's expansion and the mysterious force known as dark energy. Type Ia supernovae serve as standard candles, objects with a known intrinsic brightness that allows astronomers to measure cosmic distances with high precision. The discovery that the universe's expansion is accelerating, based on observations of distant supernovae, revolutionized cosmology and led to the proposal of dark energy as a dominant component of the universe's energy budget. Understanding the nature of dark energy remains one of the most significant challenges in modern physics and astronomy. Beyond observational astronomy, theoretical frameworks like inflationary cosmology and string theory offer potential explanations for the universe's structure and evolution. Inflationary cosmology proposes that the universe underwent a rapid expansion phase shortly after the Big Bang, smoothing out its initial irregularities and setting the stage for the formation of galaxies and large-scale structures. String theory, a theoretical framework seeking to unify quantum mechanics and general relativity, posits that fundamental particles are not point-like but rather tiny vibrating strings of energy. While these theories remain speculative and challenging to test experimentally, they provide frameworks for understanding the universe's fundamental properties. The search for extraterrestrial life represents another frontier in astrobiology and planetary science. Astronomers study exoplanets, planets orbiting stars beyond our solar system, in search of habitable environments and biosignatures indicative of life. The Kepler Space Telescope, among other missions, has discovered thousands of exoplanets, including rocky worlds within their stars' habitable zones where liquid water could exist. Future observatories such as the James Webb Space Telescope and the upcoming Large UV/Optical Infrared Surveyor, LUVIER, will further study exoplanet atmospheres and search for signs of life beyond Earth. Astrobiology explores the conditions under which life can arise and thrive in the universe. It considers extremophiles on Earth, organisms adapted to extreme environments such as deep-sea hydrothermal vents or Antarctic ice sheets, as analogs for potential life forms elsewhere. The discovery of liquid water beneath the icy crust of Jupiter's moon Europa and the subsurface oceans of Saturn's moon Enceladus has sparked interest in these moons as potential habitats for microbial life. Future missions, including NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer, JUICE, aim to study these moons in detail and search for evidence of biological activity. In conclusion, the exploration of the universe's mysteries encompasses a wide range of disciplines, from observational astronomy and theoretical physics to astrobiology and planetary science. Each discovery, whether it's the observation of distant galaxies, the study of ancient supernovae, or the search for extraterrestrial life, expands our understanding of the cosmos and our place within it. As technological advancements continue to push the boundaries of what we can observe and comprehend, the quest for knowledge about the universe's origins, evolution, and potential for life remains one of humanity's most profound endeavors.